join as we get along, but we probably have a schedule that is reasonably tight, so I'd rather get started. Welcome to this workshop on new internetworking protocols, architectures, and algorithms. This workshop is intended to explore how diverse and wide range of applications can collectively bring new ideas and research into networks and internetworking technologies. We have an interesting program of a great keynote talk by Ken Calvert. There are 8 contributed papers and also 4 invited talks. I want to thank Kiran Makijani from FutureWay in the US, Sherman Sen from University of Waterloo in Canada, and Xiangyang from Huawei in China, who were the general chairs for organizing this workshop, and also for Cedric Westphal from FutureWay in US, Philip Dittruk from Ghent University in Belgium, Zhaming Fu from the University of Göttingen in Germany, and Mohamed Faten Zani from ETS Canada for being the TPC chairs. What I'd like to do is go straight to the keynote talk by Professor Ken Calvert from the University of Kentucky in the US. I'll get started with an introduction, and as I get started, Ken can share his screen so he can have his talk up and queued up. So Ken is the Gartner Group Professor in Network Engineering at the University of Kentucky. His research deals with the design and implementation of advanced network protocols and services. He is well suited to talk at this workshop because he's been working on active programmable networks for a long time before and has experience there, and also has looked at ephemeral state processing and also ChoiceNet as part of the future internet architecture, which was an effort to encourage innovation through competition by developing what they called an economy plane for the future internet. Currently, he's working on developing an interface for the information-centric network paradigm. He's been an associate editor for IEEE ACM Transactions on Networking. He was earlier a faculty member at Georgia Tech and was also a member of technical staff at Bell Telephone Laboratories in Homedale, which means it was before it became AT&T Bell Labs. He is a member of the ACM and a fellow of the IEEE. Welcome, Ken. Please go ahead. Thank you very much for agreeing to give this keynote. We can see your screen. We can't hear you right now, Ken. Or at least I can't hear you.
Mute. There we go. Okay, how about now?
Yes, we can hear you. Thank you very much. Go ahead.
Okay, thanks,
Floor is
KK.
yours.
Thanks for that introduction, and thanks for the invitation to speak this morning in my time zone. Let me start my timer here so I have a clue what's going on. I want to start by saying thanks not only to the organizers, but also to some of the people I've worked with over the years on the things I'm going to talk about. And this work was supported largely by NSF, but also by DARPA and some from Intel and Cisco. Of course, mistakes and crazy ideas are my responsibility. So we're going to talk about the bottom line first. I'll give you this is something I learned at NSF, the bottom line up front, and a little bit of background about what I mean by interdomain and some things I've worked on that you've never used. as KK said, I've been trying to do this for quite a long time, trying to think about ways to improve on the network layer or the internet layer. And then we'll look at a couple of things that you probably have used, innovations that actually did get deployed. And then we'll kind of compare those things and look at success factors and focus then in the rest of the talk on one success factor that I've come to the conclusion is fairly crucial for making progress in this area. So, bottom line up front, the interdomain interface is the waist of the hourglass, and that's the internet protocol, of course. But in particular, the part of that that is used between service providers. And changing that interface is hard for several very good and logical reasons. But the fact is that there hasn't been very much innovation in that space for about 20 years. And if you look at the RFCs issued that have to do with actual protocol specifications on the wire for that, there just aren't very many. The ones that are there, some things like secure BGP, actually haven't been deployed very much. And an observation that I made when I was preparing this was that if you look at this figure, the waist of the hourglass, if you hold your head a little bit differently, you could also say that it's a bottleneck. And that's kind of the thesis of this talk. In the most recent SIGCOM, they accepted 53 technical papers. I counted one paper on anything that had to do with interdomain topics. And so innovation is largely confined to the intra-domain level or outside the actual protocol world. So the proposal is that we need to innovate in the ecosystem, and it's really the ecosystem that that needs to be updated in order for us to be able to innovate in the interdomain world. So when I say interdomain, what do I mean? So I'm sure everybody knows this, but the internet is a network of networks. And I'm going to use the term autonomous system, AS, provider network, domain, all of those I will use interchangeably. I hope you don't get too confused, but they all mean the same thing. It's the infrastructure owned by somebody who's in the business of providing network services. And that might be an enterprise to provide it for their own people, or it might be a commercial service. Sometimes we talk about access networks, which are the edge networks, which connect directly to the end users. And sometimes we'll talk about transit networks that serve other networks. And virtually every connection traverses multiple autonomous systems on its way from source to destination. So essentially every packet crosses one of these interfaces between ASs multiple times, okay, as it goes through the internet. Those are the freight carrying packets, the packets that actually do the real work, like connect a subscriber to a web server or things like that. The wire interface is, of course, IP, and the routing interface is the Border Gateway Protocol, BGP, which has been around since 1994. But the other interface is the business interface between providers, and that is completely unspecified in the protocol architecture. It developed organically, it just kind of evolved over time, and as a result, it's about as simple as it can possibly be. It's in the sense that it hasn't had much standardization activity around it, and providers don't like to talk about their business relationships. It's a competitive advantage or a competitive aspect. And so as a result, it's very coarse-grained and it changes very slowly. So that's the background. And let me say, by the way, I'm not monitoring the chat so that I don't get distracted, but it maybe somebody, KK or someone, if you can watch the chat for me, and if there's any questions, feel free to interrupt. But I hope there will be time at the end to take questions. So I'm going to talk about three things that came out of the active and programmable networking work that we did from the mid 90s to about the mid 2000s. Okay, so I'm going to be using some slides that are about 20 years old in many cases. So the idea of this programming, of this program, which was a DARPA effort in the mid 90s, was to enable new services by putting information infrastructure on the technology curve. And this was when Dave Tenenhouse was director of the DARPA Information Technology Office. And I heard him give a talk with that title in about 1993. And he made a bunch of predictions, and essentially everything that he said has come true. And I've always remembered that. So the idea was to do for network infrastructure what was going on in the computing world in terms of Moore's law and software benefiting from advances in general purpose computation. So there was a whole bunch of research questions around this. What's the programming model? How do you make this secure? Who gets to program the network? Is there a killer application for this? And if so, what is it? So let me just stop and make sure I can get feedback. KK, can you just say something to make sure you're hearing me and everything's going okay? Because I don't have any way of getting feedback at this point.
Hey, hello. Yeah, we are listening and we are having everything so fine.
Okay, great. Thank you so much. So the first one is composable active network elements, or CANES. And this was a project that we were just trying to show that this was a reasonable idea, putting application knowledge and network knowledge together in space-time somewhere out in the middle of the network. Okay, and we looked at various applications of this, including application-specific adaptation to congestion, in-network transparent caching, and reliable multicast. So we demonstrated all of these applications. A couple of things that we wanted to be able to do was not penalize traffic that didn't need custom processing. So we wanted to have hardware implementation of the fast path. So we defined a generic forwarding function to that end, and I'm going to say more about that in a second. And then we wanted to be able to reason formally about composition of the code that was injected into the network. And this was user level programmability, because we wanted the application to be able to give advice to the network. And so we wanted to be able to show that those things were correct. And we had a particular compositional approach where you would prove the generic forwarding function correct, and then have sufficient conditions so that the code that you attached to that function would maintain correctness. So the generic forwarding function was just what you'd expect. You have incoming channels to the router. There's a forwarding loop, which is the basic thing that you would expect, which I'll say more details in a second, but it had slots in it to which you could attach your code, and there might be more than one piece of code attached to each slot, to any slot, or there might be nothing attached to each slot. And then there were outgoing channels. So if you hold your head right, this looks a lot like a programming, network programming model that is popular today. So the generic forwarding function looks like this. You parse the packet, you get source and destination identifiers. You could specify a particular forwarding table that was previously set up. There's some other parameters. You check whether there's authorization, so some access control, and then a pre-lookup slot and a post-lookup slot where you look up each destination. So this was generalized unicast where you could have multiple destinations. And you construct a list of outgoing interfaces. And if you get nothing, then you send back a notification, and you might do something different. If you put user controlled code here, and then you check for congestion of each outgoing interface. And this is where we implemented intelligent discard for certain applications, application-specific discard policies for congestion control. Or then finally, there was a pre-transmission slot. So this just shows performance of the intelligent discard for MPEG video. So this is late 90s, early 2000s. So I think this was MPEG 1. But the idea is there are certain frames in MPEG that are more important than others. And if you drop frames, you want to protect those more important ones. And if you have to drop one of those iframes, then you don't bother forwarding other frames that depend on that one. So that's what this top curve is. It's the most sophisticated. And the lower ones are slightly less sophisticated ones where, for example, you simply prioritize iframes over others, or if you drop one part of a frame, you drop the entire frame without paying any attention to whether it's an iframe or a P frame or B frame. So this shows that under overload conditions, you could actually do better. And we showed that the quality of the experience was better using this discard. So that's Keynes. Second thing, Concast service. So this, at the time, there was a thing called IP multicast, which was a scalability mechanism. So a single multicast address could represent an arbitrary number of receivers, right? And so the sender would send one packet and the network would take responsibility for tracking where the receivers are. Receivers would have to signal to join the multicast group, and the network would know where they were, and it would duplicate and deliver the packets to the receiver. So this has benefits for both for the sender, which doesn't have to deal with all of the receivers individually, and the network, because it saves bandwidth, because each packet only goes over a link one time. The problem was that a lot of the applications, especially those that needed some amount of reliability, required some kind of feedback. And the feedback, there was no corresponding service, and that was the idea of Concast. So instead of having each sender send feedback individually, which breaks the abstraction and causes implosion at the sender or at the receiver, which was the multicast sender, Concast would provide a corresponding inverse abstraction, so kind of inverse multicast. And a Concast address would represent an arbitrary number of senders. And the network, as the senders all send messages, the network would actually compute with the messages that were sent and merge them according to a specification provided by the receiver. And we defined a simple 4-function API. So the receiver would supply code, Java or some other kind of mobile code, for those 4 functions, and the routers along the way would execute those, and the receiver would end up getting a single packet or some form of distilled information as a result of those sending thing, of the sender sending all of their messages. So again, there's benefits to the receiver because the implosion problem goes away, gets handled in the network, and this the receiver also, or the network saves bandwidth, at least transmission bandwidth. So this is useful for a bunch of ways. We demonstrated audio and video stream merging in the network instead of having to send everything to a centralized host the way we do today, the way that we're doing right now. You could do this in an application independent way or in an application specific way. So telemetry is a big topic today, and you could aggregate telemetry from, say, thousands of hosts so that the recipient, the receiver only gets a representative or a summation of the information that they send. We also talked about duplicate suppression, which is a very simple, that's the simplest, that's sort of inverse multicast, right? If you think about the opposite of multicast, it's everybody sends the same message and the receiver gets one copy, or aggregating small packets. And we had a paper in ICNP 2000 about doing that for TCP. We showed that it would be effective even if you didn't deploy it everywhere. So this was measuring the number of packet transmissions, packet hops, to collect a value from every one of a group that had up to 2,500 members in a 4,900 node graph. With when you deployed it only at the end systems, that's the top curve where you have a lot more bandwidth consumption, versus only at the egress nodes of each domain or everywhere. And you can see that the difference between everywhere and egress nodes is very small because of the natural funneling effect at the egress from a domain. So that's Concast, and that's actually my favorite one of these three. That and ephemeral state processing, which KK mentioned at the beginning. So the idea here was to have a less ambitious service, a very simple building block service, and let packets leave state at networks. Okay, now both of the previous ones also involved state, but the idea here was, how do we make that scalable? Because the conventional wisdom was user state at routers in the middle of the network is not scalable. And we didn't want to change IP forwarding. We wanted this to be alongside IP and not instead of, or not changing IP. So we tried to take an IP-like approach with bounded resource requirements in a very simple service. And we wanted this to be flexible and useful for solving multiple real problems. So the fundamental thing here was the notion of this ephemeral state store, which is a time-bounded associative memory, a set of tag value pairs, essentially a key value store, except that it was time bounded. So you would put a pair in and it would remain for some number of seconds and then it would evaporate. And this was a per interface service. And then there would be an instruction set, which each packet could carry at most one instruction in a shim header or an option in the IP header or something. And those instructions would be the equivalent of assembly language instructions, where they would operate on values in the state store or fields in the packet or node specific values like certain MIB variables, for example. And it would interact in the forwarding operation only in the sense that you could cause the packet to be discarded. So that was the only way you could affect the forwarding path. And then you would construct end-to-end services by sequencing packets in time and space. And so this shows the idea of the ephemeral state store. So there were put and get operations. If you did a put at this time, you could get the value out for some limited amount of time. The time constant was tau. You could change the value. You could rewrite it, but after that time, you would get null because the value's gone and it's never refreshed. Okay, that was an important characteristic in terms of the engineering of this thing. So we implemented this thing on the IXP 1200 network processor and later ported it to the IXP 2400 processor, and in a way that was transparent to the router. So you would stick this at the interface and it would capture packets as they came in or went out from the router. And so you would implement this per port. And these are numbers from a talk I gave in, I don't know, 2005 or something, about the estimated throughput based on the number of micro instructions required for two different instructions of these packet carried instructions. So a counter and comparing two values. So, and we did an SRAM, an implementation if you used SRAM, which was pretty expensive, or if you did it in DRAM, which was slower, or some combination of the two. So you could use this to control packet flow. You could do a lot of the same kind of things you could do with Concast, but this was presumably a little bit easier to implement and a little bit less scary because of the bounded resource requirements, and it could be engineered to keep up with line speeds. So you could find multicast branch points, you could do aggregation of feedback from a large group of nodes, et cetera, et cetera. So those are three things that I worked on in the early, like I say, 2015 to 25 years ago. There's a whole bunch of other things that I or other people have worked on that I don't have time to mention. Postmodern internet architecture was part of the NSF FIND program. We did a complete from scratch redesign of the network layer. Integrated services and the resource reservation protocol got a lot of attention in the 90s and 2000s. I don't think you've used that lately. You can't buy that service unless you use it for it's out there. You can use it for a VPN, but at the retail level, the quote unquote retail level, you don't see it. Genie, a lot of people thought would evolve into the next generation network platform because of its virtualization capabilities. That hasn't quite happened. Genie is still around and some people are still using it, mostly for teaching these days. Information-centric networking, I know several of you are familiar with that, seen a lot of attention. The future internet architecture projects from the NSF program, Mobility First, XIA, Nebula, and name data networking, and let me not forget the other one. Well, anyway, secure BGP is actually a standard, and it's there are RFCs about route origin attestations so that route hijacking is harder. It's had a hard time getting deployed, and maybe the reasons for that I think are instructive. I may not come back to that because I don't have time, but the question, it's a question of incentives, right? It's a question of motivation. And then there's a couple of things. Scion over in ICNP, the keynote speech is by Adrian Perig, who's been working on Scion for several years. And that's an interesting update of the network layer, mostly focused on security. But I really think that's an interesting approach. And then IP multicast, which, as I mentioned, used to be a thing. It never sort of achieved orbit in the interdomain world. But recently I've seen a couple of articles about the possibility of deploying IP multicast. It's certainly supported in routers. Okay, so let's talk about a couple of things that you have used, maybe without being aware of it, because they're transparent, okay? So content delivery networks, I'm sure all of you are aware of these. Bruce Maggs gave an excellent keynote at the ICN conference a couple of weeks ago. I took some of this information from his talk, so thanks, Bruce. But the original motivation for Akamai was just to reduce page load times for web commerce sites, because there's a well-known correlation between page load times and conversion rate. So you can see the y-axis here is conversion rate or click-through, or at what rate do people actually order things, and it drops off pretty rapidly as page load times increase. And there's three different types of traffic here: desktop, mobile, and tablet. And the idea was to put the content servers near the eyeballs. And this didn't actually change the wire interface between domains, okay? They did this completely within the existing architecture, but I'll say in a second why I include this as an innovation. And today CDNs provide many services, and they leverage their huge infrastructure, which they've been able to deploy, and they serve 3 terabits of HTTP, 3 trillion HTTP requests per day. And that's just Akamai. The other one is software-defined networking, okay? And this I took from a talk by Nick McCune, who was the keynote speaker at ICNP last year, talked about this. And his way of talking about this is that the idea is to enable network innovation to be sped up by taking routers from the control of router vendors and opening them up. I think of this as doing for routers what the industry standard architecture, IBM's ISA, did for personal computers 30 years ago when they opened it up and commoditized PC components. And the same thing has happened with server components in data centers. And commoditizing the hardware and using open source software enables the owners of the infrastructure to save CapEx. And the claim is they can also save on OpEx because of reduced complexity, the ability to evolve their network faster, and experiment by writing their own software. And this is kind of progressing in two phases. A programmable control plane and programmable data plane is becoming a thing now. Originally, it was all about the control plane. Today, data planes are getting more and more programmable and looking more and more like the kind of things we did in the active networking program 20 years ago. So let's compare these two things you haven't used and innovations you probably have used in terms of some success factors, okay? So the first thing is technology. So implementing canes in the 90s and early 2000s, it would have been very hard. It would have been impossible to compete with IP to do things in software at that time. Concast, you might have been able to do that with today's network function virtualization platforms. The hardware is caught up with the processing requirements. And again, we implemented ESP on a network processor. You could have done it with an ASIC. Even with the network processor, you could keep up with relatively low speed links. A CDN, on the other hand, the technology was there. You could implement it with off-the-shelf servers, network equipment. You didn't have to change anything, and all you had to do was buy adequate off-the-shelf hardware. Software-defined networking was enabled by so-called merchant silicon, these switch chips that were very inexpensive, and made it possible through a whole bunch of startups and also the operating systems that ran, that controlled those things. So you had open source and merchant silicon and things like the protocol independent switch architecture that came along and actually made that possible. It's a much narrower programming interface, but we'll come to why that doesn't matter in a second. Second thing, thrust. This was a term I learned in the IETF. It's just it means people pushing for adoption of something. So the saying was more thrust, Scotty, more thrust. In my projects, look, I'm an academic. I didn't have the resources to attend all the IETF meetings. We did present Concast at one time to the Reliable Multicast Research Group in the IRTF. But multicast went away, so there wasn't very much point in pushing Concast if you didn't have multicast. Again, for ESP, we were academics, and so that's a lot different from people who actually have a stake. And today, people start startups. Akamai was a startup at one point, and there were others. That's a competitive business, so people actually have a stake, a personal stake in seeing things succeed. So I think that's a huge factor, right? As comparing an academic exercise to a commercial success. And today people start startups to get their innovations deployed. And then third, and probably most important, is the motivation for deployment. So there have to be clear and quantifiable benefits, and they have to accrue directly or indirectly to whoever is paying for the deployment. So for the things that I talked about, they were going to benefit the end user. That was the motivation. But the people that would have to deploy them, the network operators, didn't have any way to charge for them and to make sure that only people who paid got access. Okay, with Concast, we actually did solve the access control problem with a secure version of the setup protocol. But ESP, for example, was designed to be too cheap to meter, as they say. And so what was the benefit to the deploying internet service provider? with CDNs and SDN, again, we talked about the well-known relationship between the speed and the conversion rate for content delivery networks. And in SDN, it's the reduced CapEx and potentially reduced OpEx, although that may be controversial. I'm not sure everybody buys that. But the point is that SDN is deployed intra-domain. So the operator is the one who has to absorb the cost and also gets the benefits. So there's a direct motivation for the operator to deploy it to get these benefits. For CDNs, in addition to this speed up, that's the business opportunity. There's also an aspect of this, and this is where I think CDNs deserve to be considered an innovation. The CDN deals with multiple content providers. So the money flows from the content provider into the CDN enterprise, the CDN business. They deal with multiple ISPs, they deal with multiple colos, and they deal with hardware vendors. So those are their cost, that's their cost of goods sold. And again, I stole this from Bruce's keynote, but that simplifies the life of both the content providers and the ISPs because they only have to deal with the CDN. They don't have to deal with, a content provider doesn't have to deal with many ISPs. So this was essentially a new money flow in the ecosystem. And that I think is the big innovation of content distribution networks. And that's why I included it, because that is, in my mind, the important aspect of that's blocking improvement in the interdomain regime. So there's a story that Dave Clark tells that I'm sure many of you have heard when he had a conversation with a well-known economist. And the economist says, the internet's about routing money and routing packets is just a side effect. And you guys screwed up the money routing protocols. And Dave says, I didn't design any money routing protocols. And the economist says, that's what I said. And so my point and sort of my thesis is the importance of routing and forwarding money in the internet. So just as kind of a reminder, in today's internet, money only comes into the system at the edge, right? Subscribers, whether they're businesses or residential users, they pay their access provider. The access provider, depending on how big they are, they may have to pay a regional provider. And then there's the tier ones at the top, which they're the ultimate connectivity providers, right? And so money only flows up, and this constrains the packet flow. It constrains competition because the edge is where people have the least opportunity to compete, to make choices, because in a lot of places it's a monopoly or a duopoly for the local provider. And so we don't see very much innovation that's visible at the edge of the network. And this, in my opinion, is the crux of the problem. So ISPs just have no incentive to support new end-to-end services because they don't get an advantage because there's no way for them to collect, to benefit directly or indirectly from deploying those services. So as a consequence, end-to-end innovation is confined to the intradomain area. And you see a lot of activity around wireless and data centers. Look at the papers in SIGCOMM, management of intradomain of provider networks, network telemetry, that kind of thing. Or you see new ecosystems developing like in content delivery networks. Okay, so my thesis is we need some kind of interdomain money routing and forwarding mechanisms. And I kind of came to this conclusion after our ChoiceNet project, which was actually a regular NSF award for several of us from UMass, NC State, Renzi, and University of Kentucky. And the idea was to build an economy plane for the internet, okay? And there were several pieces of this. One would be a marketplace where customers can choose providers. and providers can make offers to customers, okay, and contracts. And then there would be ways to set up these services in the network once they were contracted for. Now, we did some of this, but we didn't get all the way to the money flow protocols, okay? But the hypothesis was that competition would drive innovation. So if you give the users the ability to vote with their wallet, and you encouraged providers to offer alternatives, and if users could tell whether they got what they paid for, then that would lead to more innovation, more choice, and more innovation as competition developed. So this project was actually grafted onto the Future Internet Architecture program. It wasn't one of the original projects, but NSF said, this is like a Future Internet Architecture, so we're going to have you be a part of the program. So I'm going to spend the rest of my small amount of time talking about a potential driver application for this. And like I say, we're kind of still working on this. We had a follow-on project about something on economic software-defined exchanges, and I'll talk about that in a second. But the idea is to create a spot market for interdomain connectivity. So transit providers, of which there are honestly fewer and fewer as the internet flattens out, but their load is somewhat predictable, has a predictable diurnal effect. You've probably seen that. And so they have unused capacity at some certain times. And there was a paper by Bao-Chun Li and one of his students showing that under certain reasonable assumptions, transit providers could make additional profits by selling their unused capacity, their spare capacity. And they would sell this to edge ISPs so that edge ISPs could provide cheap transit for their elastic traffic. So traffic that it can be moved around in time. So for example, backup traffic. So the idea of the spot market was to sell this capacity cheap. So transit providers need to be able to figure out their available capacity, distinguish revenue generating traffic that's sold on the spot market from other traffic, which they could do with software defined networks. Access providers need to figure out how much they can sell, how much they need, how much their customers need in terms of elastic demand. And then they need to choose among offers. And there needs to be some kind of brokering service or matching service to propagate these offers and match them up. So that implies we need standard interfaces, because standard interfaces lower the transaction costs. And the whole idea here is that instead of the very high transaction costs that we have today with interdomain business arrangements, that would be lowered by having a standard interface. And what does that look like? So our proposal is to have IXPs, interdomain exchange points, act as a neutral third party in this ecosystem. So providers interface with what we call economic software defined exchanges. So these are IXPs that use SDN. And with SDN, they can have rapid setup and tear down of flows. And providers would talk to ESDXs instead of having these one-off interfaces with each other, okay? Now the business relationships between providers would still exist and they could still be secret. It's just that they would be brokered through the ESDXs. And the ESDXs would have to be a trusted third party there. So the ESDX would collect and propagate the transit connectivity offers, collect the access provider acceptance, and instantiating the forward state. So this, if they took a BGP-like approach, it would look something like this. So the hexagons here are ESDXs, inter-exchange points. The clouds are service providers, and each service provider connects to ESDX. The ESDXs that connect to access providers advertise which ones they're connected to. So we're talking here about getting traffic from B to A. So that's what's being advertised. So then the providers get that that advertisement and decide what they want to charge if they have spare capacity, and then they forward that to the other IXPs that they are connected to, and they forward the offers to further providers. So now Gamma has advertised service for a cost of 3, which has reached B, and Epsilon here takes the offer of Delta and adds its cost onto it for a total cost of 2, and that gets propagated. So B then decides it's going to take that offer, and that acceptance gets propagated back through the network. And as it propagates, the flows are set up through the provider networks and the IXPs until in the end, the traffic can flow. So that's it. So the point I'm just trying to make is that money routing protocols are crucial, and the lack of those has continues to impede innovation in the interdomain space, and that standard economic interfaces could be a way of breaking the logjam. And I use an analogy of the shipping container, which is a standard interface between truck, rail, and ship enterprises, and allows them to have much lower transaction costs in stringing together the services of getting stuff from one part of the world to another. The idea is that once you have such a service, such a broker and clearinghouse that would also handle payments, it could be used for all kinds of things. And finally, the last point I want to make real quick is that interdomain to intra-domain evolution is easier, I think, than the reverse. Okay, so that's a hypothesis. But I would remind you that in the beginning, the IP started out as an overlay network. It was intended to be in gateways between different kinds of local and wide area networks. And there actually were commercial networks in the at the time IP came around in the early 80s. But as the technology got better, as these blocky gateways evolved into modern lozenge-looking routers, those underlying technologies faded away and were replaced by IP as people realized they could build their local networks with IP routers. So it went from interdomain to intra-domain, and it became the network layer instead of the original internetwork layer that it was designed to be. So maybe that could happen with other kinds of services, other kinds of end-to-end services. So that's it. Thanks very much. I think I went over my time a little bit. Sorry about that. Maybe I have time for 1 or 2 questions.
Sure. Thank you very much, Ken. Really appreciate giving the talk. Folks, anybody who has questions, please ask on the chat window or unmute and speak, and that's fine. In the meantime, maybe Ken, I can ask a question. Can you hear me, Ken?
Yeah, I can hear you.
Okay, so if I look at providers like AT&T as transit providers, they, in terms of money flow, it almost seems like they've been disintermediated. When I was there, I found that more and more of the interactions were directly between content delivery enterprises, whether creators or delivery networks, and the end user.
Right.
And there's so little money that flows to them that there is no room for expanding or innovation. And it seems like these old traditional approach of talking about money flowing from the end user upwards to the service providers at the higher levels in the hierarchy have more or less disappeared.
Yeah, so
and it's only for enterprise type of access that there is money flow.
Right. So I think that's a great point. The death of transit, the disappearance of transit has been predicted for several years, and the flattening of the internet is a well-known phenomenon. I think a couple of things. One is that I think that goes along with the increasing concentration of the internet as a vehicle for delivering content. As opposed to a general purpose communication substrate. And I think that's kind of I think there's a positive feedback loop there, right? You're right that in some sense the CDNs have done what I was proposing that the IXPs do. As you say, they're the intermediaries, and the content providers connect directly to the access networks and just skip the transit, which is, a perfectly natural thing to do. But I think the more that happens, then the more we're just going to be dominated by content, providing. But it is a valid point. So it could be that there's just never going to be sufficient demand for the kinds of things I'm talking about. And I probably should have said that up front, but yeah, I think it's a good point.
Other questions? Another thing that struck me with your ESP was you said, look, I'm going to forbid the use of soft state and refreshing that. Why is that so important?
Okay, so that was sort of the genesis of the whole thing, was the realization that scalability of user-controlled state is not about the amount of state. It's not about the space. It's about the time-space product that's occupied by the state, right? So if you can't if you can refresh it, then you have the problem of things that stay forever, and you got to worry about. You can't really engineer the thing. You have to engineer it for the busy hour, and it's much more expensive. If after a certain time, every piece of user-controlled state has to recompete with every other one, then you can actually engineer your state store to sustain a line speed rate of creation. So that was the whole idea there.
So it's basically resource management through competition. If you're staying there, you don't have any rights beyond a certain time. Otherwise, right. by refreshing, you implicitly have some kind of a priority.
Yep, that's it. And it's, you can make it fair. And I mean, we did some work about how do you ensure reliability. There are tricks you can do with that, but and also the fact that you choose your tags randomly gives you sort of a private view of the state store, right?
Thank you, Ken.
All right.
Don't see others asking questions on the chat window, and we're also quite a bit behind already.
Yeah, sorry about that.
Thank you. No, this is good. Thank you very much.
Thanks again. I'm going to have to go because I got to go teach my class. So
okay,
I'll try to rejoin later.
Okay.
Good luck with the
conference.
You. Thanks.
Thank you, Ken. Thanks. Okay, so is the next speaker Wanli Zhang? Are you ready? Can you please have your slides up?
Yeah, I'm ready. Thank you.
Okay, thank you. So we'll move on directly to two contributed papers that we'll have in this session before we break. The first one is by Wanli Zhang, Xiangyang Gong, Tian, and Jifan Tang from BUPT in China, which is to look at high-speed route lookup for variable length IP addresses. And Wanli is a master's student right now in computer science at BUPT. And he's a member of the State Key Laboratory of Networking and Switching Technology. And his interests are in innovative network architectures and intent-driven networks. Take it away, Wanli. Go ahead.
Okay, thank you. Good morning, ladies and gentlemen. I'm Wanli Zhang from BUPT. I'm very honored to share my study on route lookup for variable length IP address. Since the advent of Internet, IP addresses have been the core of it. However, with the rapid development of Internet in recent years, IP addresses are facing more and more problems, such as address exhaustion, low packet efficiency, and low flexibility. The reason is that IP addresses use a fixed length design. The new IP network architecture and addressing method were born to solve these problems. Based on this architecture, the addressing scheme adopts variable lengths and structured addresses. The address space can be smoothly expanded according to the network style without modifying the old network address configuration. A new IP address consists of several address segments, as shown in this figure. Each segment is a natural number without an upper limit theoretically. We use dots to separate different segments. For example, 1.2.3.4.5 is a new IP address with 5 segments. When using new IP for communication, devices in the same line differ only in the last segments. The gateway device of a line stores the same prefix of the devices in the line. Therefore, devices in the same line can use very short addresses for communication. Also, a device can communicate with devices in different lines using a long address with more address segments. As shown in this figure, only the last segments of the complete address is used for communication between devices A and B within the line. When the device A communicates with an external server, the destination IP address of the data packet is a complete address, and the source IP address still reserves the last segments. The data packets pass through when the data packets pass through the gateway device, it supplements the source IP addresses to complete addresses, and the data packets are routed to the server through the backbone network. Similarly, the destination IP addresses of the data packets constructed by the server is complete addresses, and the source IP addresses only retain the last segments. However, there are some challenges about the new IP, and the greatest one is the route lookup of variable length IP addresses. In order to solve this challenge, we mainly made 2 contributions in this paper. Although the new IP address space is large, the routing table of each router only stores a small part of it. By analogy with IPv4, its address space is the 32nd power of 2. It is about 4 times 10 to the 9th power, according to the data published by CEDAR report. The routing table size of backbone routers is about 9 times 10 to the 5th power. Considering that new IP address use a structured design and assign IP based on the geographic location, new IP can make routes aggregated better. So we can believe the new IP address prefixes in the routing table to be very sparse. Therefore, we propose a new IP address route lookup mechanism using binary cams and ternary cams. Binary cams are used to map each segment of new IP address with variable length to a shorter and a fixed length address. Then we use ternary cams for longest prefix matching. First, we split the new IP address into segments and set up a separate binary cam for each segment. For a binary cam, we assign a binary digital label for each entry from small to large. In this way, we rename a label for each segment address so that a long segment address can be replaced by a shorter label. Then we splice these labels in the order of the segments. Finally, a complete binary digital label address is obtained, and it can replace the original new IP address uniquely. A problem needs to be pointed out is that there are obvious separator dots between the segments of a new IP address, but the label addresses are all represented by binary numbers. We need to separate the labels of different segments to avoid ambiguity. For binary cams, we set the length of each label in the same segment to the same, but the length of different segments can be different, depending on the number of stored entries in the binary cam. As the routing table is updated and the number of entries changes, the label length of each segment will also change to accommodate a larger number of entries or shorten the width of cams. In this way, each segment can be separated in the label address without the need for a separator. Through binary cams, we replace the structured and long new IP address with a flat and short label address. We specify the mask length of a label address prefix as the length of it. By storing label address prefixes in the ternary cam in order of their mask lengths, the storage of new IP address prefixes is completed. When a new IP data packet needs to be forwarded, the destination address is converted in the same way. But if a certain segment address fails to match in the binary cam, we can use a specific unassigned label to represent the segment without matching. By entering the complete label address into the ternary cam, the longest prefix matching result can be obtained. However, given that there is no upper limit for the length of new IP addresses theoretically, so there may be some extremely long addresses. The proposed mechanism in contribution 1 requires that TCAM width should not, ternary cam width should not be less than the length of the longest address, which results in a waste of ternary cam storage space. Considering that most addresses are much shorter than the longest address, we can map these long addresses to a short address space through a hash function. Therefore, we propose a long address shortening method to reduce ternary cam storage space consumption. In this method, we use two ternary cams to store short addresses and long addresses respectively. The ternary cam that stores short addresses is called ternary cam 1. The ternary cam that stores long addresses is called the ternary cam 2. If the length of a label address prefix does not exceed the width of ternary cam 1, it can be stored directly in it. Otherwise, we hash the portion of the label address that does not exceed the width of ternary cam 1 into a short value. When this value is connected, then this value is connected as the previous part with the excess part of the label address and stored in ternary cam 2. When the destination address in a data packet is converted to a label address and the length does not exceed the width of ternary cam 1, only ternary cam 1 needs to be queried. Otherwise, as shown in this figure, we split out the part of the label address that does not exceed the width of ternary cam 1 to query ternary cam 1. At the same time, The label address is processed based on the same method as the long address prefix, and is queried in ternary CAM2. If ternary CAM2 has no matching result, the longest prefix matching result is the result of ternary CAM1. Otherwise, it is the matching result of ternary CAM2. We evaluated the performance of the proposed new IP route lookup mechanism from two perspectives: lookup latency and the ternary CAM storage space consumption. For normal addresses lookup, it takes 1 clock cycle to look up in binary CAMs, getting the label address, and another one for lookup in the ternary CAM to obtain the longest prefix matching result. The lookup latency should be equal to 2 clock cycles, but our lookup method can apply pipeline technology. Therefore, the new IP route lookup mechanism can obtain a longest prefix matching result every single clock cycle. We estimate the relationship between the size of the routing table and the width of ternary CAMs. According to the data released by CEDAR report, the number of BGP routing table entries in the backbone router is approximately 1 million. So we randomly generate 1 million new IP address prefixes with different number of segments as routing table entries. As the generated prefixes gradually increase, we calculate the width of ternary CAM1 required to store them. The storage space of ternary CAM2 can be ignored due to its small number of entries. In this way, a figure between the number of routing table entries and the width of the ternary CAM is drawn. The ternary CAM width required for IPv6 route lookup is always 128, which is not shown in the figure. From the figure, we can conclude that the router can choose approximate its ternary CAM width based on the size of its routing table. In addition, the new IP routing table can be aggregated on a much larger scale than IPv6 and IPv4 because the new IP address adopts a structured design and the address allocation is on the basis of the geographical location. That's all of my presentation. Thank you for your attention.
Thank you very much, Wanli. I'm happy to accommodate questions. We have a few minutes. If somebody has questions, please type it in the chat window if you're not able to unmute, or go ahead and speak if you have a question, please. Okay, let me ask a question, Wanli.
Sure.
Why do we need variable addresses as long as we have long enough addresses? Your address shortening approach that you have for being able to split it up into two TCAMs will be helpful anyway, isn't it? That you're not wasting TCAM space and so on. But it seems to me that when you have these variable address space, address lengths, and then you have to have the routers in between expand, that piece of the work can end up being quite expensive, isn't it? Lookup is one thing, but you have to now change the address on the packet as it's going through, isn't it?
Oh, yeah. As for the, do you mean that is the update algorithm will waste some time?
Will consume time.
Sure. As for the update algorithm, it is out of my knowledge of the limit, and we can email after the conference. Out of the papers talk about it. Sorry.
Okay. Okay. Other questions, please, from people in the audience?
One question. in IPv6, the IP header is fixed. With your approach, would the IP header also, let's say, varies, and then the processing storage cost is different, right? From one packet to another.
Yeah.
Do you mean that the
header size is different from one packet to another? It's yeah. So storage is another problem, that you have to prepare different size of the data structure, or making one size fit all, then you have a lot of waste. When you are queuing, yeah, because traditionally you have to store and forward, and once you store that, then you need to think about how to make the accommodate it.
Okay, it's a good question. As for the storage and forward of different size of headers, it is a future work of our paper. I'm sorry that I can't give you a good answer.
So I have one other last, it's probably a small question, Wanli, which is, what is the range for each segment? You know, how many bits do you specify? Is that fixed, or is that also variable? The number of segments is variable, but how many bits for each segment?
For each segment, at base is also variable. It will depending on the network scale.
There must be some way of making sure that, so you have to look for the delimiter of the dot, right? Somehow, when you're processing the packet. Okay, that can be expensive. Okay, thank you very much. It's an interesting talk. Thank you, Wanli. Thanks.
Thank you.
Let's go on to the next speaker, the last talk of this session. It's by Akbar Majidi. He's from the University College Cork in Ireland, and he's going to be talking about optimized joint Unicast-Multicast panoramic video streaming in cellular networks. And he's done this work with Ahmed Zahran, who I've worked with in the past. And Akbar is a postdoc in the computer science department at University College in Cork. And he got his PhD degree from Shanghai Jiaotong University in China in January of this year, 2020. And he's been at Cork since then, and he works in omnidirectional video streaming, data center networks, SDN, NFV, and machine learning to contribute to congestion control. Go ahead, Akbar.
Hello, everyone. Really, thank you for your kind introduction. So you can see my slide, right?
We can see your screen, not the slides yet. We see maybe the LibreOffice. Yeah, now, yes. Go ahead.
Yeah, thank you. I'm so sorry. Thanks for, again, your introduction. Yeah, my name is Akbar Majidi. I'm a postdoc at UCC now. I work in MISL lab, and we got the funding for this work from Huawei. This work was done with unlimited support of my supervisor here in postdoc program, which is Dr. Ahmed Zahran. Really, I would like to appreciate him. He really support. Otherwise, I couldn't done this in short duration. As you mentioned, I just joined here a couple of months ago, 8 months ago, so after my PhD. Okay, in this talk, I'm gonna illustrate optimized joint Unicast-Multicast panoramic video streaming over cellular network. I mean to say how we can use both Unicast and Multicast in the same time for sending some, huge amount of data. Is it possible or not, and how? Okay, as you are aware, 360-degree virtual reality and the augmented reality technologies are really gaining popularity because this kind of technology takes user to the different atmosphere environment, so immerses users so into the virtual sense. So they really use this, and this, as you are aware again, this applications known as a 5G killer. So I want to say, as we know, 360-degree images are roughly 3.5 times larger than the usual videos, and hence we need to send at least Ultra HD resolution for this kind of videos, at least Ultra HD resolution, 4K, 8K, 24K. So this requires really high demand of bandwidth than any other kind of videos. So the thing which have done so far is they say that let's split the videos to the different tiles, if you can see here in my screen. So let's say this is the whole panorama, and we have split this whole panorama to the 5x5 here tiles. So the known approach for this is they say that let's send the field of view for each user. As we are aware, each user, when they use head-mounted display, they have different view in the panorama. So like field of view for the user one is here, which he is requiring 4 tiles. However, field of view for the user 2, he is requiring, you see that, 6 tiles differently. And some of tiles are overlapping each other. Imagine if we can have the same panorama in 200 or 1,000 people where they are watching the live 360-degree, like, let's say, match. So most of this tile will overlap. The idea over here said that, okay, since the tiles are encoded independently and field of view for each user are different, so why not using the joint unicast and multicast approach? Like we are sending the overlap tiles through multicast, and some of the edge tiles, let's have a look here to the field of view of user 2. This tile will unicast for just this user because no one is interested in this tile. So by doing this, we can reach different we can reach better battery consumption and bandwidth. We can solve the bandwidth problem. There is huge things. Let's go on. I will talk. As we know, we have multimedia broadcast multicast services. So multimedia broadcast services standardize the architecture of delivery mechanism of content to a large number of users in a cellular system. So the content is delivered over one or more base station, and by having this EMBMS, we can say that okay, I'm gonna send this tile over a multicast, and the rest of this tile for this user unicast, and this one is unicast. The simple question is, why not sending all of this tiles multicast? Because by using EMBMS or multimedia broadcast multicast system, the quality will set with the least channel quality indicator of the user in the group. So let's say we have 10 users in the same group. One of the user has the least channel quality. So we need to set that group with the least quality of that user. So we cannot serve all the users or in the same group by the high quality or medium quality. So the idea is we optimize this problem and to solve that, how we can give some of these users a tile independently, just specific tile, to have not least quality for the same group. I hope it's clear. So the objective over here is maximizing the total user experience. So we formulate the joint Unicast-Multicast delivery of panoramic video, which we called jumps, as you can see here, as an optimization problem for a group of users. And we did diverse experiment you can see in the paper. So we have two constraints. One for ensuring resource are limited to the available resource blocks in the base station. And the second constraint is for ensuring every user receives every tile just once, not multiple times from different technologies. So the objectives and constraints are linear in the problem binary variables. Thus, we can solve it by integer programming solver. So I used Groovy optimizer by using Python. So jumps leverage the independence of the encoding and the diversity in the field of user and channel quality indicator to improve both network utilization and user experience. As we are aware, if users need to listen to all multicasted tile, they need to use more energy, battery consumption, I mean, and use more resource block in the base station side. So, however, we are sending some of the tiles unicast per user, so we don't listen to all multicasted channels. So this is it would be smaller than the total number of resource blocks, and we expect to reduce the user battery consumption of the user by listening the fewer resource blocks. So our solution offers which tiles need to multicast and their corresponding quality. Let's say we have different tiles, and we say that okay, from this tile need to send quality 1, quality 2, quality 3, or best quality, and the other tiles which need to unicast by this quality to that user, specific user. This is the simulation setup. We used a different number of users for having a diverse simulation. So I used 5, 10, 20, 40, and 80 number of users. So the panorama bitrate which I used, 6 megabits per second, represent the quality 1. 8 megabits means the quality 2. I'll go through them. 10 is quality 3, and 14 is the best quality, which is quality 4. And these are the number which we got from the standards. This is the panorama resolution. Then tiling configuration, you can have diverse tiling configuration. We used 8 times 8 because most of the papers said that this is the tiling has the best solution. If we use so little, I mean 2 times 2 or 4 times for panorama tiling, it's not really economic. If we use like 64 times 2 for 64 times, we will have some more bits. So this is need to be adjusted well. So we use 2 groups of channel quality indicator, like group 1, which is the bad quality, let's say, from 2 to 7. And the second group is 8 to 15, which is the, this is the representation of the channel quality indicator numbers, which varies from 2 to 15, different quality, and the spectral efficiency corresponding. If the user have channel quality indicator, let's say 2, it means it can stream 20, or if he has 15, it can stream 733 megabits per second. So this is the rest, and we use the custom-built Python for the simulation. We compare jumps with Vrcast, the well-known paper in the literature. So we use, as I said, we use Groovy 9, and we run each result 50 times to get the average and the solution. So we present the result of the following. Sorry. scenarios, we have had 4 different scenarios. DWL represent a user with diversified field of view when user is looking everywhere by having weak channel condition, which I mentioned 2 to 7, and limited resource block. We don't have abundant resource block in the base station side. The scenario 2 is DGL, which is user again looking everywhere by having good channel condition, but again limited resource block. The third scenario which we simulated is user is again looking everywhere, like you know the difference. When user is looking, this is adventure video, user would like to look everywhere, but if it's the soccer play, everyone is focused in somewhere. Where is the ball? So in the scenario 3, user again is looking everywhere by having weak link condition and but abundant resource block. And the final scenario which I'm going through them is the user is focused, good link condition, and limited resource blocks. Okay. This is the first figure for DWL scenario. So as you can, this is the this figure. Let's have a numbers here. Figure A1 plots the stack bar cumulative distribution function of tile quality and illustrate that jumps. This is the hash bar is represented jumps. Can in the 5 user case, we send roughly 38% of the video by quality 1 and 30% over here by quality 2, which is 8 megabits, and this is represent the quality 3, which is roughly 22% and 10%, let's say, by having best quality. However, in the same case, VRcast, which I say that this is the state-of-the-art algorithm in the literature, has no at all quality 4 for the same scenario. And if we go further in figure 1b, which plots the field of view bitrate of the cumulative distribution function as a stack bar plot for 10 percentile across all simulated group size. So as you can see that jumps facilitate higher field of view bitrate than VRcast. In every user configuration, the field of view bitrates are vary from 20 to 60%. User is higher than the highest bitrate supported by the VRcast one. Additionally, jumps also boosts the minimum field of view bitrate for all scenarios except the 80 users case. I'll go through them by. So this is the figure 1C. It plots the 10 percentile stack bar again. So as you can see that jumps use fewer resource block than the VRcast model. So if we go through all the simulations in different scenario, as you can see that over here we have little bit here best quality and more quality 3 than VRcast, and so on over here. In the 80 user we have Q3, but there is no Q3 at all here, and we use more Q2, let's say, and so on. So this, because of the timing, it's 15 minutes, it's finished already. Now this is the rest of the scenario, which we can see that in all different scenario we have the best result over the time. So we introduced a new resource management scheme for delivering popular content after 360 degree by using Multicast and Unicast jointly in the cellular networks for improving the system. So our evaluation showed that we always have a significant improved than the others, and for the large group, we maintain the high performance as well. So we are planning to extend our work by having the single frequency networking and etc. etc. I'm sorry, the time has passed. If you have any questions, I would love to really try my best to answer.
So if others have a question, please go ahead and speak. or type it in the chat window or session Q&A. Let me ask a question, Akbar.
Yes.
If I look at a field of view for an individual user, I see that some of the tiles are going to be sent using EMBMS, and those tiles might be at a different quality than some of the other unicast tiles, correct? So does that mean that in your approach you might end up having a particular user's field of view have some combination of multicast and unicast, and they might have different quality representations?
Yeah, this is perfect to the point question. Yes, this is right, but we leverage our optimized problem somehow, which we cannot have some part of the video by having best quality and the other part with the lowest quality. So we try to have, at least closer quality. Some parts, yes, true, we can have like quality 2 and quality 3, but not quality 1 and quality 4.
So how do you incorporate that into your optimization to say that you will not accommodate diversity more than one quality range difference? I didn't, because it seems like here you are trying to show the improvement with jumps by saying that I actually accommodate a larger number of quality ranges, right, for users. So it seems actually you're allowing for greater variability in the quality for a user. And so, that is your figure of merit.
This is a perfect question. These things I hope I could able to respond. The thing which we have done is, let's say we have 8x8 tiles, 64. So in this group, we have tens of users or hundreds of users. So some of these users has least channel quality indicator than the average. So we cannot give in the same group different quality at all. We need to set the quality to the least quality. So if my quality is just Q1, everyone needs serve. If you have the best channel quality, you need to got by the least channel quality. I mean quality of those streaming. So we tried to serve some of those users in the same group by unicast, by having the much higher quality to be average in the groups and serve whole group with the average quality. We cannot serve, by multicast different quality for different users or different types or with different qualities. We just tried to give some of the tiles to some of the users by unicast to not have the least quality for the same group.
Right, but you're not trying very hard to make sure that a particular user has all of the tiles in his field of view to have the same quality.
This is not true. We cannot serve, let's say, in hundreds of people in the same group, one user with the high quality while we are using EMBMS. We need to use, because the coding is different. So if your channel is perfect, you can encode different, high quality, while we are in the same group and my channel quality indicator is low. So I cannot decode that quality. So they need to serve with my quality. Since you have the higher quality, you can got the low quality. So this will be same to all others. We are trying to give some particular users by unicast to have at least the average quality of the group, to not sacrifice the others, which while they are having the better quality quality indicator to not giving the least quality.
Somebody else with questions? Okay. Thank you very much, Akbar, for your talk. I think this is the end of our session. There is, I think, a half-hour break, and then at the local time of 12:30, we'll have the next session. And Zhang Fu, program chair, one of the program chairs for the workshop, will be the session chair. So please contact him for the next speakers.
Thank you.
Zhang, go ahead, Zhang.
Yeah,
You can
I'm
take
here.
over.
Yeah.
Okay.
Right.
All right.
Okay.
Thanks.
Do we continue to use this window, or it's a different session, by the way?
My understanding is this continue to use this window, but Francesco, can you say?